Welcome back. So in this video, we're going to be going over the study guide for your Apex Geometry course, Lesson 1.4, Introduction to Proofs. And so whenever we're talking about proofs, we want to make sure that we cover a few basic terms about the creation of proofs, just so that we're all on the same page. Just because this language and vocabulary comes up often whenever we're actually writing proofs, so we want to make sure that we're using those terms correctly. So in page 1 of your reading and slide 1 of your study guide, right, the first thing that we want to do is actually just define what a definition is. And so a definition is a precise statement of the qualities of an idea, object, or process. So let me write that out. So it's a precise statement of the qualities of an idea, object, or process. And so this basically means what are the key characteristics that makes something what it is, right? So if I had to provide a precise statement about who I am, right, this precise statement would kind of capture who I am and would really characterize just me and would help separate me from like someone else, right? So definition is just a really precise or really careful way of describing something so that it's distinguishable from other things. So on page 3 of your study reading and slide 2 of your study guide, we also want to define another term called a postulate. So a postulate is a statement assumed to be true without proof. So we don't need to prove it. So let me write that down. So it's a statement assumed to be true without proof. And another word that we can give for a postulate is an axiom, right? So the term axiom and postulate are used interchangeably. So I'm going to give 2 examples of a postulate, right? So an example of a postulate in geometry is it's a line segment. So a line segment can be drawn between any 2 points. Okay, so that is an example of a postulate in geometry because whenever you have 2 points, you can just draw a line through them and then boom, you have a line segment. So that's something that you don't really need to prove in order for it to be true, right? That's literally what it is. A real life example of a postulate is something like Barack Obama is the 44th president of the United States of America, right? That's a true statement that I don't need to prove to you is true, right? This is just a fact that you believe, right? So you can think of a postulate kind of like a fact. It's not something that you have to put in a lot of work to use because it's already kind of accepted as true, not just by you, but like by generally everybody. So you might be wondering, okay, why are we talking about definitions? Why are we talking about postulates and stuff, right? So the main reason why we need definitions in order to write proofs is just because you're not always going to be working with people who had the same teacher as you or who took the exact same course as you, right? So we use definitions as a way to kind of standardize what we're talking about. So that, let's say that you're trying to prove something to someone else on some like geometry topic or really anything, right? You want to make sure that you're using the same kind of language and that you're on the same page in order to make your point, right? So the whole reason why we use definitions is definitions allow all people involved in the proof to know they are talking about the same things. And it would be helpful if I spelled that correctly. Right. So let me give you an example, right? So let's say that you're doing a proof about triangles. And so you want to make sure that you're on the same page with the person that you're talking to about what a triangle is, right? So if your definition for a triangle is that it's a polygon with 3 sides, then when you're talking to the other person, then they will able to accurately understand that you're talking about that shape that they know is a polygon with 3 sides, right? They're not going to be thinking about a square or a circle or anything like that, right? Like you're on the same page about exactly what you're talking about. And that's the whole reason why we use definitions, because it's a precise way of kind of characterizing something so that we don't get confused and take it as something else. So on pages 9 and 10 of your reading and on slide 4 of your study guide, you're given a diagram, and we want to kind of fill in the blanks to label the 2-column proof with some of the basic things that you will typically have in your 2-column proof, right? So the first thing that you want to write is your given statement. So your given statement is A, and it's the facts that you're given. So you want to assume that everything that's written in there is true. And let me make that a little bit bigger so that you can kind of see that a little bit better. And I'm going to change the formatting a bit. Let's change it to be right there. There we go. So whenever we're writing any given statements, they're just facts that are given to us in the problem, and we're just going to assume that it's true. And our proof statement B, is what we want to prove. That's pretty straightforward, right? So let me change the font in that, and also change the formatting as well. There we go. Okay. So in our left column of our 2-column proof, right, we have our statements, and it's a series of deductions to get from A to B. So we're using deductive reasoning in order to move us along in this proof. And so these statements follow logically one after the other, and you're going from the very general to the very specific in order to prove your case. So your A should be your most general statement, and then your B should be your specific statement that is specifically proving what you need to prove, right? And then your right column, it states your reasons for each deduction. So just so that everyone knows, like, oh, this is, where I'm getting this information from. I'm not just getting this out of left field, right? There's a reason why I'm stating this specific statement. And then at the end of our proof, we write QED, right? And this is written after the last proof, after the last step to show that the proof is done. So let me just fill in that blank. The proof is done, right? And so this is kind of our conclusion, right? We're saying, okay, we're done. No need to look further. And if you don't believe me, you should contact me at this point, right? I'm done with this proof, and I've proven what I need to prove, right? And it should be clear when to write your QED, because you've just given your reason for your proof statement. So let's examine page 11 in our reading and slide 5 in our study guide, right? So let's look at an indirect proof, right? For an indirect proof, we want to assume the opposite of what you want to prove is true. Okay, so you're kind of taking the roundabout approach, and you want to use deductions to prove that the opposite is false, right? So you're kind of saying, okay, well, let's say that this thing that I want to prove is false, right? So I'm going to assume the opposite of what I want to prove is true, right? And I want to use deductions to prove that that opposite is false, and so the contradiction proves that the original statement is then true. Right, so this is one way that you can go about proving whatever you need to prove, right? You can take this kind of roundabout approach to saying, well, let me look at the opposite of what I want, and if the opposite is false, then what I want to prove must be true, right? So that's one method of going about your proof. So let's look at pages 14 to 16 in our reading and slide 6 in our study guide. So it says fill in the blanks to complete the flowchart. So whenever we're doing proofs in specifically geometry, we want to use definitions, postulates, and axioms, right? Write that. Axioms, and I'm going to make the font a little bit bigger so that we can actually read it, and I'm going to format it differently. Right. I want to use definitions, postulates, or axioms, and common notions to just prove a statement's true, right? That's our step 1. And then our step 2 is that the statement is now a theorem, right? So once we've proven something, we can now say that it's a theorem, that we don't have to prove it again, right? Because the proof has already been done. And so once we have a theorem, then we use the theorem to prove corollaries, so kind of supporting theories or things that are related to it. Change the formatting, and let me fix the spelling, right? We want to use the theorem that we prove in order to prove later theorems called corollaries and other related statements, right? So let's actually kind of define what each of these words mean, right? So whenever we have a theorem is a statement that's been proven true, right? So a statement that has been proven true. And this is opposed to a postulate or an axiom, which is just something that we accept as true. Theorems are something that we actually have to put in the work and prove is true, right? And so a corollary would then be a statement that makes sense based on a theorem, right? And so an example of this might be something like Okay, so an example of this might be something like you have a theorem that's saying if you have parallel lines and a transversal crossing through them, then the corresponding angles are going to be congruent, right? So a corollary of that might be that if you have corresponding angles that are congruent, then you have two parallel lines. So those statements are related to each other, and one was created based on the other, right? But a corollary is just a special, it's a related type of theorem to the theorem that you originally proved. Okay, so let's go on to slide 7, and we're looking at page 15 in our reading, right? So let's actually complete this proof by writing a justification below each box, right? So our first statement is our given statement. So it says a car is driving east, right? And then the statement that we say following up is a car is facing east. So a justification that I could write for this is that, well, if the car is driving east, then cars drive in the direction that they're facing. So we could say that a car drives in the direction it is facing. Okay, so that's my justification for it. And that's a justification that makes sense for that statement. Let's look at my third statement. So if I say a car is facing east, then I say all the cars are facing east. So I might want to imagine this like there are a bunch of cars in a lane together, and they're all facing the same direction. So if all the cars are in one lane, then they're going to face the same direction. So let me write that cars in one lane face the same direction. Okay. And then my final statement, or my conclusion, is that none of the cars are facing west, right? So I'm just going to use kind of like common sense based on my previous statements, right? That cars can't face two directions at one time. So if they're all facing east, then they can't be facing west, right? So my reasoning for this is just like common sense, where it's cars cannot face two directions at one time, right? Or two like opposing directions. So let me write that. Two opposing directions at one time, right? And I've just completed the proof by creating justifications based on what I know about the situation. And so that's an example of filling out a proof. Let's go to slide 8, and we're on page 16 in our reading. So we want to create a flowchart proof to show why Macy's chickens will not provide milk, right? So we have this person, Macy, and she's trying to say that chickens provide milk, but we're saying that no, Macy, that's not correct, and we want to actually show her why she's wrong. So let's look at this, right? So we have some facts about chickens and mammals. So we know that chickens have feathers, no hair, and lay eggs. And our second fact about chickens and mammals is that all mammals have hair and produce milk. Some mammals lay eggs. So our starting point should be that we want to just kind of establish the fact that Macy has chickens, right? So let's just say that Macy has chickens, right? So Macy has chickens. Okay, because we're trying to talk about like why Macy's chickens will not provide milk. So I need to establish that Macy does have chickens in the first place. So my first statement is just that Macy has chickens, and this is just a given statement, right? Because I'm looking at Macy's chickens. Then my next statement might be that chickens don't have hair. So let me say that chickens don't have hair. Don't have hair. And this was based on my first fact about chickens, right? And so I can say given, or I can say that chickens do not have hair. Either one works. So I'm going to say given fact about chickens, right? Because that was a given fact about chickens. All right, so let me try to think about what should be my next logical step. So I want to somehow connect the fact that So let me just think about my next logical step. So I just said that chickens don't have hair, right? And the reason why I picked hair is because that seems to be the key feature about mammals, that mammals have hair and produce milk. But I know that chickens don't have hair. So I want to make a connection somehow between the fact that chickens have no hair and that all mammals have hair and produce milk. So because chickens don't have hair, I guess a logical conclusion I can make, or a logical statement I can make that follows, is that because chickens don't have hair, then it can't be a mammal, right? Because all mammals have hair and produce milk. So I'm going to say that chickens or specifically, let me just ground it in Macy's situation. So Macy's chickens are not mammals, right? And the reason why I can say this is because I know that all mammals have hair, right? That was one of my facts about chickens and mammals. So all mammals have hair. Okay, so if it's not a mammal, then I know that if all mammals have hair and produce milk, and because Macy's chickens are not mammals, then Macy's chickens do not produce milk, right? Because those two ideas go hand in hand. So then I will say Macy's chickens will not give milk, and the main reason being, here, let me make that font a little bit smaller, that all mammals produce milk, right? So only mammals produce milk. And I already established in the previous statement that Macy's chickens are not mammals. Okay, so that's one way that I can actually do this proof, right? You could have given slightly different justifications, but we're mainly pulling from the fact that we were given these two facts about chickens and mammals in order to complete this. Great, so let's move on to page 18 and 19 in our reading, and we're going to just finish off the study guide on slide 9, right? So we just want to fill in the blanks for these two. That's just talking about the definition. So a blank is a statement that has been deductively proven and can be used as a reason in future proofs. And we said that a theorem best matches this definition, that it's a statement that has been deductively proven. So it's something that has to be proven using deduction and can be used as a reason in future proofs, right? So once we have a theorem, we kind of put it in our arsenal because it's something that we can use later on in future proofs and in future problems where we're trying to solve for something. And then finally, a blank is a statement that is very obviously or easily deduced from a theorem. It also can be used as a reason in a proof. And like we said before, that's what a corollary is. Corollary, there we go. And a corollary is just basically, you can think about it like a baby theorem, but it is still a type of theorem, right? You still have to kind of prove it, and you're proving it based on a related theorem. Okay, so hopefully this was helpful to you. I know that proofs can be a really intimidating part of geometry, and it's something that a lot of people do struggle with. So if you have additional questions, just email me, and I'm happy to give you extra examples or walk through some of these examples a little bit more with you.